So let's talk about quantum Fourier transform again. So let's review. So what are we up to? So we have a function that sends n bit string to n bit string, and we want to find the period r. And of course, we kind of assuming that the period is quite large, but quite big also. I mean, actually, even if period is small, in order to find that that's the real period, let's say you find that the numbers are iterating after 4 numbers. So you might say r equals to 4, but we really don't know until you find out all the numbers at the end. So even if r is small, you cannot really sure whether the period is that until you see the end of the values. So anyway, so we assume that the n is quite big. That means 2 to the n is like almost a number that is almost impossible to find out the value of function entirely. And r is fairly small, so that if we find the period or candidate of period by using the quantum Fourier transform, we can verify it by taking the few sequence in the front. All right, so what is the circuit? We have Hadamard, and we have nothing here, and we have Oracle, and we take the measurement first, and then we take quantum Fourier transform, and we take the measurement. But actually, we don't, I mean, yeah, so we take a measurement here, but this measurement is just to take the period, just to make, just to kill everything else except what that is periodic, right? So, what was it? So let's see. I forgot to bring my notebook. So, what was Zj represent? So Zj. So if the measurement outcome of, let's see, Zj is about the measurement outcome of so it slipped out of my mind. Which one was Zj? Just can't remember it right now. Is this one Zj or that one Zj? Which one? This one or this one? They're both bottom. No, this one? Okay, so this one is that. Okay, so the output register is Z, which is Zj, which is the integer multiple of 2n over r plus delta j, where delta j is less than half. Then what happens? So by this equation already, so we have z over 2n minus j over r is less than delta j over 2n, right? So it's 2n plus 1. So we know this. So again, so this is something we already know. We take the measurement, we know what z is, and we know what n is, because that's the circuit. But we don't know what j is, and we want to know what r is. So we don't know anything about this ratio, but we know at least both of them are rational number, and it satisfies this equality. So this is known, and this is unknown. So how do we even find out? I mean, if we know that there are two rational numbers whose difference are smaller than something, how do we find out the exact numerator and denominator satisfying this equation? So at this moment, we have to use the continued fraction, which is come from the number theory. So we're gonna spend entire class to talk about this continued fraction, and it's not gonna be. I mean, the material that I'm going to cover is like 100 years old. So, and also it wasn't anything to do with the quantum Fourier transform or quantum algorithm at all. It's just a number theoretic fact. And miraculously, it is very important to conclude what R is from that place. And it's just very clever to find out that there is a connection between number theory and the quantum Fourier transform. So anyway, so let me just define what the continued. So when we're going to divert a little bit to continued fraction and then come back later to finish the argument. So let's see. A continued fraction anyone want to find, if you want to know the Korean word, and it's called 연분수, is a rational number given by, so it depends on whether your continued fraction is finite or infinite, but mostly when we say continued fraction, we just call it a rational number by, so PQ given as A0, 1 over A1, 1 over A2, and so on until we get a, let's say n plus 1. Okay? So the index doesn't matter, I mean, but most of times I'm going to use the index up to n plus 1, so that's why I put n plus 1, but you can finish at the 1 at n here. So you can imagine if you take the, you know, common denominator again and again and again, so you're gonna get some number integer over integer. So imagine these are all the integers, and mostly it's positive integer except for a0. So if you have a negative rational number, you can make a negative integer at front and then make everything else as a positive integer, and nothing is 0. Okay. All right. So so this is common way of writing the continued fraction, because we cannot make a ratio, so because we're gonna make a lots of space. So instead, we're gonna just write the sequence of these numbers to indicate that's the rational number. And also another common way of writing this continued fraction is that you can abbreviate these fractions into one line, single line expression, like this one. So just a notation, okay? So here's an example. Well, I think it's too simple, but let's make it continued fraction. Yes?
Is a n plus 1, I mean, n plus 1 중에 다 아래.
Yes, so somewhere in below.
그러면 n plus 2개의 숫자를.
Yes, basically we have n plus 2 numbers. I mean, but index doesn't really matter. I just wrote that way because I want n to be bigger than 0, or it could be negative. I mean, if the number is just integer, we don't have anything here, right? Just integer a0. Yeah. So let me give an example. I mean, it's not gonna be familiar to you, and even for me, every time I see anything about the continuous fraction, it's sometimes confusing. So, let me give a hands-on example. So what is this? How do I make it into continuous fraction? So continuous fraction is somewhat like a way of expressing a rational number, or even just a real number. So here we have 2 over 1 plus 2 over 5. That's one way. So we know that a0 is 1. And the next part is we need to make 1 over something, right? So it's a 1 over 5 over 2, right? And then I want to make 5 over 2 into something plus 1 over something, right? So it's 1 plus 1 over 2 plus 1 over 2. And we're done. There's nothing I can do from this moment. So I can have 1, 2, 2 as my sequence. 1, 2, 2, right? However, I didn't say continuous fraction has a unique expression. So you can trick a little bit. So I can say it's 1 plus 1 over 2 plus 1 over 1 plus 1 over 1, right? So I can still say this is also continuous fractions. So 1, 2, 1, 1. That makes sense, right? And another, so even another way of writing this is it's 1 plus 2.5. Okay, so I didn't say, I mean, in number theory, since they are always dealing with the integer, we presume that AIs are integer, but matter of fact, this AI doesn't have to be even an integer. It can be any number. So I can say this is the continuous fraction 1 and 2.5. So this is also possible. Okay. And I want to just show you the interesting fact about this. So we have another example. How about we take the continuous fraction of irrational number? So although I said the continuous fraction is a rational number given by this, if I take infinite sequence instead of finite, then I can write continuous fraction of irrational number. So let me make a remark first and then give an example. The continuous fraction can be given by an infinite sequence of integers to represent a real number, not only the rational number. So I can write A0 is my first integer, A1 and A2, and I can go forever. So here's an example. Let's say my x is square root of 2. So we know that it's something like 1.414, and goes forever, right? So let's try to make it into continuous fraction. So we have 1 plus 0.414. Right? And then I can say, okay, maybe I need what? So I need 2 plus something, right? So if I want to make 0.4 something, I think 1 over 3 point something is too small, right? Because it's 0.333, something like that. And 1 over 1 is also too big because it gives me, so a number whatever goes into here, let me just write it here. We have 1 over 0.414, right? So I know that it's just it's 2 point something, right? So I know that it has to be 2 plus something here. Okay? I mean, 2 plus something means that it's a 1 over something. So I know that it's 1 over something, right? So, and then what is this? So let me see if I can do this. So how much is this? 1 over 0.4 is probably...
So it goes to about 2.414.
No, it's 1 over 0.414. Did you calculate the reciprocal here? So it's a 2.414. Oh, okay. So 2.404. So so I need 1 over 414, something like this, right? So if I do this, then I think it's getting the same number always. So I get 1 over 2 plus 1 over 2 over something. But then you can see that there's a same pattern here. So this the decimal point is exactly the same as 0.414. So it's iterating. So 0.104, 414 and infinite appears every time I do this. So you can imagine that this continued fraction will always have 2 as an integer part here. So you can say this is 1. If I have to write down square root 2 as a continued fraction, this is the sequence that goes forever. So it is also possible to write every number, even a rational number, as continued fraction. So what do we want to talk about? So let me define one more terminology and write the theorem, and then try to prove the theorem and along with other corollaries. So here, definition. Let's say x, whatever that is, could be rational number or irrational number, is represented as continued fraction of a0, a1, a2, a3, and so on. So you have a sequence of integers. The continuous fraction a0, a1, up to an. So we don't miss any of this integer sequence. You only take the first n or n plus 1 or n plus 2 in this case, let's say. But because I want to make it up to n plus 1, just take the finite sequence, okay? Then this continuous fraction is called the convergent of x. So actually what we are doing here is, as we take more and more integer sequence from beginning, we get closer and closer value to the original x. So I can give you an example. So let's see. If my x is square root 1, is continuous fraction because it has only one element. And 1, 2 is also continuous fraction. So this is 1, and this is 1 plus 1 over 2, which is 1.5. And let's see another one, the next one. And we have 1, 2, 2, which gives me 1 plus 1 over 5 over 2. So it's 5 over 7, right? So 5 over 7, so how much is it? 1.4, right? So you can see this number, 1.414 something, will always in between two consecutive continuous fraction of the sequence. So these are all called convergent of square root 2. So if I can go forever, right? There are infinite convergent of this number. All right, so as I mentioned the definition here, I can state the theorem. So what is the theorem? So if x minus p over q is less than 1 over 2q squared, then p over q. So here, x can be any real number, and these are rational. Okay. That's the condition. Then p over q is a convergent of x. So that's the that's the key theorem that we need to use for finding the period. So before I move on to prove this theorem, let me go back to our preliminary. So what did we have? We had something similar, not exactly same. What we had is z over 2n minus j over r less than 1 over 2n plus 1, right? That's what we had. So we know that this must be something about x, because that's what we know. And this is something that has the same role of p over q. But then this something is weird. I want same inequality, 1 over 2 times q squared, but we have this. So what we're going to assume here is that r, the period, is actually less than 2k, where n is an even integer, a multiple of 2. So in that case, x minus j over r is now, of course, it's less than 2k times 1 over 2, but 2k is bigger than r, so we can say this is 1 over 2, 1 over r squared, right? So we have exactly same equation, inequality here. X, which is already known in its rational number, in our case, is the difference between x and this number is less than that. It's exactly same situation here. So what can you conclude? So, I mean, this is already what we know from our quantum circuit. So, but there is one condition, that z must be of the form zj, and we also show that there is a more than 40% chance to get such j. So I'm not saying that you always get such j, but you might assume that this z is of the form zj, and then try something with the same with this argument, and then if it turns out that it's not really period, then maybe that is not of the form of that j. So you can try it again, but at least will you get the more than 40% chance that that j is that j, and then you will have actual this situation. So once you have it, then by the number theory, the theorem here says that this is a convergent of z over 2n. So how do we apply this? So we're going to prove this theorem, but let's postpone this a little bit and then try to conclude our quantum circuit part. So here's an example. Let's say, let me make sure that I have numbers right. Yeah. Okay, so here, let's say n is equals to 14. So that means 2 to the n is equal to, how much is it? So it's not given here. 1,000 for...
16,384.
Yeah, 16,384. Okay, so this much. And let's say we have z equals to this much. Okay, it's all possible. So we know that x, which is z over 2n, is 16,384, 11490. And let's try to find continued fraction, because assuming that this is of the form zj, okay, so I want to find out what j over r is. Since the theorem says j over r is a convergent of the x, we need to find the entire sequence as a continued fraction. So if you do this, I'll just give you the answer here. So 1, 2, 2, 1, 7. So you can, no, it goes forever. Goes even more. Sorry, so it goes 7 and 35. So it will stop at some point because it's a rational number, but so this is enough to find out what J over R is. So once you have this, we can try to imagine that J over R is one of these convergents. So we try one by one. So let's say J over R, pretend that J over R is, let's say 1, 2, 2. Okay? So how much is it? Yeah, so it's 1 over 2 plus 2 plus 1 over 2. Sorry. 1 over 2 plus 1 over 2. So it's 1 over plus. Let me write down the fraction first and then 0 point what? How much is it roughly? Can anyone calculate? 0 point what? 71, something like that. Okay. All right. So let's pretend this J over R was this convergent of the continued fraction of x. So let's see whether this satisfies the inequality. So if then let's see, 11490, 16384 minus 5 over 7. How much is this?
Minus
0.013. So how much is, so we know that this must be less than 1 over 215, right? So this, how much is this? 1 over 215.
.05 times 10 to the minus 5.
Okay, so we're gonna use this number many times. So inequality is certainly not true, right? So it's not true. So therefore, this cannot be, the J over R cannot be discontinued convergent, right? So this is the inequality that we must satisfy. It's not still correct. So what we can do, the next one, right? So instead of taking 3, we can take 4 and so on. But let's say we take 7. So let's try 0, 1, 2, 2, 7. Okay. And how much is this? We can have so this one is 54 over 77, right? So what does that mean? So J is 54 and R is 77. Okay, so 77 is a nice number. And let's see if it satisfies the inequality. How much is the difference? One 11490, 16384 minus 54 over 77. How much is it?
Times 10 to the minus
6, okay. So it's less than this, right? So it satisfies inequality. So that's okay. I can have this as a candidate. And actually, this is the final stage, final step you can go. You cannot take convergent whose sequence is longer than this. So let's see what happens if I take one more step from here. So let's say J over R is equals to 0, 1, 2, 2, 7, and the next one, which is 35. So if you take the ratio, it is what? I think you have to take it, sorry. Getting complicated. So I want the ratio so as a rational number. So let's try this. So it's 1 plus 1 over 2 plus, so let me write this way. It's an easier description here. So 1 plus 1 over 2 plus 1 over 2 plus 1 over 7 plus 1 over 13. So if I do this, I can say this is 1 over, the next one is 7 plus 1 over 35, right? So it's 35 over 7 times 35 plus 1. So it's, how much is it? Well, anyway, this much, right? So and then, so we have 1 plus 1 over 2 plus, and the next one is 2 plus this much, 2 plus this, right? 2 plus this. So we have, what is it? 7 times 20, 35, 210. So 246. So we have 246, 2 times 246 plus 35, right? No, is it right? So we have, no. So it's, yes, right. So we are taking this. Yes, right. So we have this, and how much is this one? 492 plus 35. We have 527. Okay. So then we have 1 plus 1 over 527. 2 times 527 plus 246, right? Yeah, so 246. And I think at this moment you don't have to carry on it anymore. So anyway, so if you do this, then what's gonna be the denominator? It's gonna be 2 times 2, 527. 527 plus 246 and something here. So something here, right? So you can say that R is now almost 1,500, yeah, something like that. So it doesn't matter what the exact value is. So we know that R is more than and bigger than 1,000. So remember what we assumed here. So we assumed that R is less than 2K. So here we have n equals to 14, so therefore we have k equals to 7. So R must be less than 2 to the 7, which is 128, right? So at here, we already found that R must be 77. I just did one more step to see if is there any other R that satisfies this. So if I take one more step, what happens is I get the larger R, but this R is not less than 128. So this cannot be the radius, period, right? So not because the difference is less than this, but because the number, the denominator found from the convergent cannot simply satisfy our assumption. So this cannot be true, right? So we have unique R. You can find a unique R satisfy inequality and our condition here. You can always do that. So again, under what assumption have we concluded R is equal to 77? The assumption is that the Z here, which is 11,490, is of the form of ZJ, whose difference between the number is less than half. So if that is true, then the period is 77. But that might be wrong, right? So you have to check. So these at least have more almost 60% chance of of being wrong answer of the period. So but imagine that you can go through first 77 numbers in your sequence and then see and maybe the twice of that length and see if that's the period. So it's not at all hard. I mean, it's relatively easier to go through all the like 16,000 numbers, right? So it's saving lots of computational complexity here. Does that make sense? So all the procedure here. Any questions about this? So you might ask, oh, what if the denominator getting at some point smaller, becomes smaller? There's no chance of doing that. So denominator, if you increase the number of sequence in your continued fraction, the denominator and numerator always increase. We're gonna show that in the proof of that theorem. So yes. Then P and Q, you mean this one, these two? No, you can't. That's from the number theory. Yeah. You always get a coprime numbers. Okay. So you have a question?
Can I tell you this? Can I tell you?
A number? Okay, so what's the number? One.
It must be less than one.
So what's the denominator here?
Denominator 1605.
Oh, 1605 and
1078.
10?
1078.
1078. Yes. Thank you. Any other questions? All right. So, since I made lots of hiccups in the proof of the theorem in the class, so I'm going to make up my mistakes by recording this part. So we're going to prove this theorem about the continued fraction and its convergence. So if you have this inequality, theorem says that this P over Q is a convergent of X. So being convergent of a number is that if you take a continued fraction of that number, then this number, P over Q, appears as one of the subsequent of the continued fraction. So that's called convergent. So proof goes this way. So we're going to take P over Q minus X to be something of this form, 1 plus minus 1, because it could be negative, over Q squared times delta. So it says it's less than 1/2 of that number, so delta could be in between 0 and 1 over 2. It cannot be 0, it cannot be 1 over 2. And let's write our P over Q to be a continued fraction up to an plus 1. So I like the index up to n plus 1 because it makes it easier to state other theorems about continued fraction. So let's say this is Pn plus 1 over Qn plus 1. So from here, now I think I made a hiccup at right here. So what I'm going to do is we're going to assume that my x can be represented as follows. We suppose that x is given by some omega times Pn plus 1 plus Pn over omega Qn plus 1 plus Qn. Okay? So once we suppose that, so I can take any omega that satisfies this inequality, whatever the x is, there should be some omega that satisfies this, right? I mean, I don't know about Pn and Qn, but if I choose omega wisely, if you take the equation write the equation in terms of omega explicitly, then omega is a formula in terms of x and Pn plus 1. So you can find what omega is. So I'm not saying omega is an integer. I'm not saying omega could be positive. It must be positive. It could be negative, whatever, right? So I can find some omega satisfies this equation here. So then what happens, I can plug that in here, inside of here, and let's see what happens. So it's plus minus 1 q squared delta, and this is Pn plus 1 over Qn minus plus 1 minus x. And if you plug that in, let me replace that here. Then it's omega Qn plus 1 plus Qn and omega Pn plus 1 plus Pn. And let's make a common denominator. We have omega Qn plus 1, Qn, and Qn, and Pn plus 1, omega Qn plus 1, and Qn, minus Qn plus 1, omega Pn plus 1 plus Pn, right? And then you can get a cancellation of these two. And what happens here is omega Qn plus 1 plus Qn plus 1, and Pn plus 1 Qn minus Qn plus 1 Pn. Okay. And after finishing this proof, we're going to show one lemma that says if you have this thing, then it's always given as minus 1 and plus 1. So in fact, it's about the difference between the ratio and Pn, actually n, right? So it's just n here. And then the remaining part here are the same thing. Here we have omega Qn plus 1 plus Qn and Qn plus 1. Okay, so compare the left and right. So we have plus and minus 1. We don't know, but this right-hand side, plus minus 1, determines the signs on either side. So we can say that this part are taking care of this plus minus 1 here. So we can get rid of these two canceled out. And here we have q, but I replaced q by q plus 1, so I can say it's q plus n, Qn plus 1. So let's write in terms of delta. Take the Qn plus 1 square on the right-hand side. We get Qn plus 1 divided by W, Qn plus 1 plus Qn. And if I also write down in terms of omega, so omega is now 1 over delta minus Qn plus 1. And now look at what about this? So 1 over omega is always bigger than 2 because 1 over delta is bigger than 2 because delta is less than 1 over 2. So it's bigger than 2. And also, if you look at the two consecutive denominator of the convergence of a continued fraction, it's always increasing. So yeah, it must be less than 1. So if you take the less than something 1, the largest number you can get rid of is 1. So it must be bigger than 2 minus 1. So it's bigger than 1. Okay, so from here, what you can say is that once you have this format, and once you have the omega part here appears in your format is bigger than 1, then your x is actually given as continued fraction whose last part of your sequence is actually omega. So a0, a1, up to an plus 1, and the last one is omega. So still, I'm not saying that omega is integer, but it's a positive number, bigger than 1. So omega could have its own continued fraction, which appears if I expand it as a finite or infinite sequence of integers, then it appears at the end of this part. And I can write that x as a continued fraction by that way. So that's actually finished the proof. So what are we going to show? What were we going to show? We wanted to show that P over Q is a convergent of x. Since we know that x is given as a continued fraction with the first integer as exactly the same sequence of P over Q, this immediately shows that P over Q is one of the convergent of x. So we finished the proof. Okay. So what we have to show is there are two things we have to show. First, why can we show that x is equals to a continued fraction of x is be given as this form if we have this information? And second, I assume that this numerator is given as minus 1 to the power of n. We need to show this. But actually, it came from a simple observation of continued fractions. So let's give some addendum to this proof as a lemma. All right, so one lemma, first lemma here is that let Pn over Qn be the ratio of continued fraction of up to an. Okay, so then Pn plus 1. So I'm assuming that there is an infinite continued fraction with an infinite sequence of integers. So Pn plus 1 is an plus 1, Pn plus Pn minus 1, and Qn plus 1 is an plus 1, Qn plus Qn minus 1. So let's prove this. So we're going to prove by induction. First, let's think about P0 and Q0. What's P0, Q0? So here, we're not talking about two numbers which has common divisor. So P0, Q0 obviously has to be just integer A0. So therefore, we're assuming that P0 is A0 and Q0 is 1. And let's think about P1 and Q1. So here, again, we are not considering its common divisor has common divisor. So it must be the integer rational number given by this formula. And we know that it's A0, A1 plus 1. So obviously, these two numbers are co-prime each other because they're so plus 1 here. So we have P1 equals to A0, A1, A0, A1 plus 1, and Q1 equals to A1. Okay, so in order to use the induction, I think I need to go one more steps here. So P2 over Q2. Let's see. It's A0, A1, A2, right? So it's A0, A1, A2 plus 1, A2, and A1, A2 plus 1, and A0, A1, A2, A0 plus A2. Right? Okay. So P2 is that, and Q2 is that. So P2 is what? A2 times A0, A1 plus 1 plus A0. I can write down that as A2 times this one, which is P1. And what is A0? It's P0. So P0. And what is Q2? Q2 is A1, A2 plus 1, but I can write as A2 times A1, which is Q1, and 1, which is Q0. So I have this equation when n equals to 1, right? So I know that the initial step is correct, and I need to use the induction method. So let's suppose that this this is true for all 1 to, let's say, n minus 1. Okay, so I can get it right to up to n minus 1. So I want to show that whether this equation is true for n, which is exactly these equations. So let's think about the ratio first. I know that it's A0, A1 up to an plus 1, but I can write it as A1 up to an, and then instead of having one more step as a sequence, I just add the value into the last sequence, so I get the first n sequence instead of n plus 1 sequence. And then I can apply the next sequence. So this is actually equals to an. So this is the last sequence in my convergence continued fraction. So I can think of this as the an plus 1 in the n minus 1 case. So an plus 1 over an plus 1 is this part. And what comes next is Pn and Pn minus 1. And that's the Pn plus 1 here. And then what's next? An plus 1, an plus 1, and Qn plus Qn minus 1 here. Oh, by the way, sorry. So it's not Pn. So it's one step behind. So it's n minus 1 and Pn minus 2 and Qn minus 2 here. So let's make it simpler by multiplying an plus 1 on top and bottom here. We have an plus 1 plus 1, Pn minus 1, Pn minus 2, and same thing here, an plus 1 plus 1. Oh, forgot. An plus 1 multiplied here, an plus 1, Pn minus 2, and Qn minus 1, an plus 1, Qn minus 2. So there should be some canceling out. Let's see. So I'm going to rewrite in terms of an here. So an plus 1 combined with an Pn and Pn minus 1 and Pn minus 2. And so I used up this part and this part. And what left is Pn minus 1. So Pn minus 1. And this part's similar. So an plus 1, an, Qn minus 1, Qn minus 2, and Qn minus 1. So since we assume that this is true for up to n minus 1, so it applies to here, right? So this is equals to Pn, this is equals to Qn. So I can write this is an plus 1, Pn, Pn minus 1, and this is an plus 1, Qn plus Qn minus 1. So what we showed here, this ratio same as Pn plus 1 over Qn plus 1. So Pn plus 1 is this, Qn plus 1 is this, which is exactly the same formula here. So we show that the next step is correct. So by induction, everything for every n is correct. So that's the first lemma. So from here, what we can show is that whenever you have whatever on at the end, you will always say you can always say that the ratio, the continued fraction given as a ratio, is given by some given by the last entry times the integers that comes from the one before the last continued fraction, or the convergent obtained by omitting the last entry in the continued fraction, right? So same for the denominator here. So that's why we could say x is given as the continuous fraction's last entry is omega, because we know that the omega is is a number bigger than 1, so we can get the continuous fraction that goes on from the last entry of continuous fraction of Pn plus 1 over Qn plus 1. Okay, so that's the first lemma, and so I'm gonna keep the lemma here and then prove the next lemma. The next lemma says we have Pn plus 1 Qn minus Pn Qn plus 1 equals to minus 1 to the power of n. So it's iterating from minus 1 and 1. So it also proved by induction. So let's say n equals to 0, and then P1 Q0 minus P0 Q1. What is it? So we know that P1 is A0, A1 plus 1, right? And Q0 is just 1. And what is P0? It's A0. And Q1 is A1, right? So we have these two cancels out, and it's just 1, right? So when n equals to 0, it's 1. It's correct. So now assume that this equality is true for 1 or 0 up to n minus 1. And I want to show that it's true for n, which means that I want to show this equation. So I know that these two are true, so I can replace Pn plus 1 and Qn plus 1 with this. So we get An plus 1 Pn plus Pn minus 1. I don't need parentheses here. That's Pn plus 1 times Qn, and Pn and Qn plus 1 replaced by this, An plus 1 Qn, Qn minus 1. So I have canceling out, nice canceling out with this and this, right? So I have Pn minus 1 Qn minus Pn Qn minus 1. And I can see that this is minus of Pn Qn minus 1 minus Pn minus 1 Qn, right? So I know what this is. So this is given by n minus 1, because it follows the formula. That's what I assumed here. So therefore, it's minus 1 to the power of n, which is exactly the same.